Okay, this is the video for test version number 3. Hopefully you're starting to get this stuff. So here we go. Design number 1 starts with 1, 2, 3, 4 white squares. Then it goes, for this pattern, 1, 2, 3, 4, 5, 6 white squares. Then it goes 1, 2, 3, 4, 5, 6, 7, 8. So looking at those 3 numbers, it looks like it's clearly going up by 2, going up by 2. That is the number I'm going to be looking for. If I went backwards and took away 2 from this 4 right here, that would give me the number of white squares at design 0, which would be 2. 2 of those white squares at design 0. What I'm doing for this problem right here is looking for all the numbers, all the equations that don't have 2 in the right place. I can see that this one clearly has 2 in that recursive form. This one has 2 right in front of x. This one has 2 right in front of x. Don't be faked out by that 4. That 4 is not the number in front of x. That 2 is the number in front of x. And then this one, you can see, this one has a 4 in front of x. It doesn't have a blue 2. This is the one that does not show this pattern. That one does not. If I'm doing the 31, I'm taking that 30 and plugging it into one of my good equations right here, or I could plug it in right here if I really wanted to, but I need to now plug in 30. So taking that equation, 2x plus 2, I'm replacing that x with the number I'm asking you to, which is 30 for this problem. I'm going to times that by 2 and then add that answer to 2. So when I plug in 30 or go to the 30th step in this pattern, I get 60 plus 2. I get at the 30th step in this pattern, I get 62 white squares. That's the answer I'm looking for. If you plugged in 30 into that equation, 2 times 30, 60 plus 2, you get 62. Again, telling you, if I went to design number 30, I would have 62 of these white squares. That's telling me, using this pattern, using that equation. All right, moving on. This one right here, clearly geometric. If you could see, kind of by maybe looking at the smaller numbers, that from 20 to 5, I'm dividing by 4. That's one way you could see what you're dividing by. Another way is dividing 320 by 80 to get 4. But no matter what, this is dividing by 4, dividing by 4. But remember again, we don't show dividing by 4. We show dividing by 4 as timesing by 1/5. That is the same as dividing by 4. Sorry, timesing by 1/4 is the same as dividing by 4. Timesing by 1/4, timesing by 1/4. If I do that timesing, it tells me it's geometric, going to be one of these exponential graphs. If I was to write my equation, this equation for recursive, f of x equals f of x minus 1, and no division, times that 1/4 right there. That would be recursive geometric. That would give you one of these exponential graphs, but dots. If I was to find the explicit one, I'm going backwards, which is the opposite of dividing by 4 or timesing by 1/4. The opposite is timesing by 4. And what number am I multiplying by 4? This 320. That will give me the number before 320, which is 1,280, which makes sense because you can see it's getting big and then going small, getting smaller and smaller. So for this equation, I take that green number and I write that first. That's 1280. I write in parentheses that 1/4, that number I'm timesing each time. And then I make sure I get full credit by putting this x up here in the exponent spot. And knowing that this is explicit, which would be a line drawn through the points that shape like that. This is geometric exponential. All right, moving on. This guy, clearly arithmetic, not making big jumps. If you need to see the number that I'm adding here, again, take just plain old 63, plain old 50, and subtract them. You'll get that number that I'm adding. I'm adding positive 13. That's the only number I could add to these negative ones and get a smaller negative number. Since I'm adding, it is arithmetic, going to be one of these straight line graphs. To find recursive, I just take that 13 and write it. So my equation is f of x equals f of x minus 1. We always write that, but for this one, I write plus 12. That is recursive arithmetic linear. That's going to be a straight line with dots. That's recursive. If I do explicit, I'm going backwards and taking away 13. And again, the number I'm subtracting 13 from is this negative 63. It's going to give me even more negatives when I subtract 13. That gives me even more negatives, negative 76. That's the number before. And that kind of makes sense because negative 76 plus 13 is negative 63. If I was to write this equation, my equation for this one, which is, whoops, this is 13 right here. Sorry about that. So I see that mistake. Always write the right number that we're using, 13. So for this one, it would be 13 times x and then subtracting that 76 number. That is explicit arithmetic. That would be a straight line going through those dots. All right, moving on. Hopefully you can hear the drum roll in the background. Here we go, playing Buena today. All right, this one is geometric. If you can't see what I'm dividing, take these two and divide them. And I'm going to take a little break here while the drum line rolls through. All right, back to the show. Thank you for your patience. So if I divide 5 by 10, it tells me that for this sequence, I'm timesing by 5. Timesing by 5. Multiplying by 5 makes this clearly geometric. If I'm going the opposite direction, the opposite of timesing by 5 is dividing by 5, or technically timesing by 1/5. And what am I dividing by 5? This 10 right here will give me the number before 10. So 10 divided by 5 gives me 2. And that makes sense because 2 times 5 is 10. 10 times 5 is 50. Now I have enough to write my explicit function. I use that green 2. I write that first. And then in parentheses, I write that red 5. And I'm raising that to the x power. That is explicit geometric, going to be a curved line with a dot or a line drawn through the coordinates. All right, here we go. This one, looking for exponential, looking for the one that has me multiply, This one right here, I could see going up by 2, going up by 3, going up by 3. That's not neither linear or exponential. It's not adding by the same amount. This one going up by 3, and then looks like it's going up by 8, or maybe not time, and then going up by another 8. That's not timesing. Even though this little bit might have been timesing by 3, the rest is not timesing by 3. That one's not geometric exponential. This one, though, I could see is not adding because this is going up by 5, and then this jumps way up to 20. This is the only one that's timesing. I could see that if I times 5 to 1, I get 5. If I times 5 times 5, I get 25. If I times 25 times 5, I get 1. 25. This is the only one that's going to be exponential. This one down here doesn't cut it either. Going up by 1, and then going up by 4, and then by 5, and then by 5. Nope, that's not a timesing one. Only the timesing ones are exponential. All right, moving on. Number 11. Again, this problem that we're doing, look for the exponentials. Look for the percents. Knock those out first. I can see this is clearly a percent. No other percent. For this version, the only exponential problem in this set is number 1. If I look at the other ones, this is just increasing by plain old 10, adding 10, adding 10, adding 10 every time. Straight line linear. If I come over to this one, it is decreasing by 3, minus 3, minus 3, minus 3, minus 3, straight line every year, minus 3. That is linear, straight line situation, going down by 3. The other ones, I got to do a little bit of math. So 9, 11, 14. I need to see how much I'm increasing by right there. I can see from 9 to 11 going up by 2, but from 11 to 14 going up by a different number, 3. So I'm not going to put 4 in linear because it's not the same amount every time. I'm going to put this one in neither. And then for these, got to do a little math. Some of you aren't doing the math. So take that $34 divided by 2 hours and see what that gives you as that rate. So 34 divided by 2 gives me $17 for every hour. Then I look at this rate and divide that, and if I get the same, then it's linear. If I get something different, it's non-linear. So 51 divided by 3 for this one gives me $17 an hour. That is the same. These are the same. That would be like plus and 17 each time, plus and 17, adding 17 more dollars each time I work an hour, adding 17. That makes this purely linear. So for this one, 2, 3, 5 linear, 1 exponential, 4 is neither. All right, moving on. This guy, find the first step by taking these two numbers and dividing them on your calculator. Type in 110.25 first, then hit the division button, then type in 105 second and hit your equal. So 110.25 typed in first divided by 105 gives me 1.05. That's going to be the number in my parentheses. That's the number that I'm timesing 105 by to get 110. That's what I'm doing right there. If I'm going up this table to find that 0, 1, up the table is always the opposite. Down the table is timesing. Going up the table is dividing. So again, what am I dividing? By 1.05, this 105. So if I take 105, the whole number, type that in first, divide it by typing in 1.05 second, that will give me the number above 105, which is 100. And that makes sense because 100 times 1.05 is 105. Now I have enough to write my explicit equation. So here I go. I take that and write that green 100 right here. In parentheses, I write that 1.05, close that parenthesis, and I rise that to the x power. That is exponential explicit. That's not going to be a dotted one. Nope. That's going to be a line with dots with line drawn through. All right, here we go. 13. Again, looking for the y-intercept. Again, the y-intercept. The y-intercept is this number right here. And again, what does that mean for this problem with rent and deposit? Again, know that that number in front of x, that represents the monthly rent. That's the slope number. That's the D number. D equals 400. If I want the deposit, this number by itself, not attached to the X, that is the deposit. That's what I'm looking for. So I'm looking for the one that talks about a deposit fee of $450. That would be that one for this situation. And of course, it's not 900. It's close to 900 if I plus them. All right, here we go. This one, a little bit different. I'm giving you what I want, and I want you to draw it. So exponential means it's going to be curvy. Continuous means it's going to have a line drawn through the dots. So if I was to draw a graph that was exponential continuous, here's a perfect example. One of these J curves without any dots. That's exponential continuous. You could have drawn it going down too if you wanted. That's exponential continuous too. You could have drawn it like that. But I drew mine increasing, going uphill, increasing. All right, the next one, I want you to draw a line that's linear, straight, but not continuous. That means a line with just dots, not drawing a line through the dots. So for this one, I need a set of dots going in a straight line. So here's one little example of a set of dots all in a straight line, linear, but a discrete form with just dots. All right, next one. I need exponential, so curve again. But for this one, I need a curve graph with dots. So if I wanted to draw an exponential graph with dots, here's an example. Maybe a set of dots that then start curving up steeply. That would be like a discrete exponential graph. If I wanted to draw it maybe decreasing, I could draw my dots like this, but again, they have to curve. They cannot be straight. Here's a better one. Most of them are these increasing ones going uphill. So that would be one that I would draw. That's exponential and discrete. All right, good luck. Hopefully this helps you.